Regents Review, Unit 5, Periodic Table. Recall that the original organization of the periodic table was done by Mendeleev, and it was organized by atomic mass. And then it was later, and the current version was organized by Moseley, and that was done by the atomic number, which we now know to be the number of protons. So the current version, again, is organized by the number of protons. Looking at the periodic table, we have periods, which are the horizontal rows, so period 1, 2, 3, 4, and so on and so forth. And then we have the vertical columns called groups. And it tells you here that these are the groups, group 1, 2, up to group 18. In a period, so going across, like say period 2 here, in a period there are the same number of electron shells. So period 2 has 2 shells, period 3 has 3 shells, period 4 has 4 shells. And we can even see that from the electron configuration that they match up. We have 3 numbers here indicating 3 shells. In a group, the vertical columns, we have the same number of valence electrons. So group 1 has 1 valence, and then group 2 has 2 valence. And because of that, they have similar properties. So an example of a question you would see on that is, which 2 elements have similar chemical properties and why? So we have Na, K, Li, and Be. So you locate these on the periodic table, and we see that Na and K are in the same group. Therefore, they have the same number of valence electrons, and they would have similar chemical properties. The broad classification of metals, nonmetals, and metalloids looks like this, as we see that most of, with the exception of hydrogen, most of our elements here are going to be metals. This small section here to the right of the staircase are nonmetals, including the hydrogen over here. Don't forget about hydrogen. And then we have 1, 2, 3, 4, 5, 6, 7 metalloids. So it's everyone on top of the staircase and the 2 in the center underneath. Okay, for some of the groups, we need to know the names of these groups. Group 1 are called the alkaline metals. And the most reactive metal we have is francium. So as we go down group 1, we get more and more reactive. Group 2 has 2 names, alkaline earth metals. In the center of the periodic table, groups 3 through 12 are called the transition metals. And these tend to form colored solutions. So the aqueous solutions tend to be colored, like the copper solution here. Group 17 are the halogens. These include fluorine and chlorine and bromine. The most reactive nonmetal is in the halogen group, and that is fluorine. And then group 18 are the noble gases. These are inert, which means they are unreactive due to their full valence shell. Recall that we do have an exception, which is helium. Helium is a noble gas which only has 2 valence electrons, where the rest of these things have 8. And the noble gases are said to be monoatomic. Since they don't bond, mono meaning 1, they just contain 1 atom. They do not form compounds. The properties of metals. Metals are malleable, so malleable metals, which means they are bendable. We can hammer them into thin sheets. They are ductile. We can stretch them into wires. Metals are really good conductors of heat and electricity due to mobile electrons. They are shiny, so they have luster. Metals lose electrons to form positive cations. And they are typically solids at standard temperature and pressure, except mercury, which is a liquid at STP. As I mentioned, metals conduct electricity because they have this sea of mobile electrons. The valence electrons are very loosely bound to the atom, and since they're moving around, we have moving charges which will conduct electricity. When we talk about metallic character, that's essentially how much like a metal you are. So metals have high metallic character and nonmetals have low metallic character. Our most metallic element we have is our most reactive, which is francium. So the closer to francium you are, the more metallic you are, and the further from francium, the least metallic. So going across a period, for example, metallic character is going to decrease because I'm getting away from francium. What are the properties of metalloids, the staircase elements? Metalloids have properties of both metals and nonmetals. So they're called the semiconductors because they're pretty good conductors of heat and electricity. They tend to be shiny like metals, but brittle like nonmetals. And one of the most common one is going to be silicon, which I showed you here and also in class, and that's used for making computer microchips because they don't lose their ability to conduct electricity as they heat up like metals do. And for nonmetals, these properties are essentially the opposite of metals. So they are not good conductors. They're poor conductors. They are not malleable. They are brittle. So when we hit them, they will break. They are not lustrous or shiny. They tend to be dull. And they tend to form anions, negative ions, because they gain electrons to get a full valence shell. So here's a nice kind of summary chart in your notes for all the properties, physical and chemical properties that we have for metals, nonmetals, and metalloids. And now let's look at the periodic trends that exist on the periodic table. The trends that they ask you about are metallic character, as we mentioned already, first ionization energy, electronegativity, and atomic radius, all listed on table S. And you're responsible to understand these trends. You don't need to memorize them because we can use table S to our advantage. So for all the trends, you just look up two elements in either a group or period, depending on what the question's asking, and locate the values on table S. And then if it's increasing, it's an increasing trend, and if they decrease, it's a decreasing trend. You're also responsible for the reasons why these trends exist. And the reasons why are these two things here. Going across a period, the trend that exists in ionization, electronegativity, or atomic radius is due to increased proton pull. So period proton pull. What that means is as you have more protons, more positive charge, it's going to pull on the electrons more. And then going down a group, the trend is due to having more electron shells. So let's look at the atomic radius first. That is the size of the atom. So if a question asks, what is the trend in atomic radius going across a period? You can pick any period. So here I pick period 2. Choose one element on the left and one on the right. I avoid the noble gases because they don't have some values due to the fact that they don't bond. So lithium and francium I look up on table S. So I see lithium is 130 for the size of the atom, and francium is 60. Since the number is decreasing, the trend is decreasing. Why? Well, going across a period, we have increased proton pull or increased nuclear pull. Electronegativity is a measure of the attraction for electrons, how strongly an atom attracts electrons. Fluorine is the most electronegative at a 4.0. So the closer you are to fluorine, the higher the electronegativity is going to be. So metals have a low electronegativity, a low attraction for electrons, and nonmetals, since they want to gain electrons to get that full valence shell, have a high attraction for electrons. Okay, so let's look at an example here, same as we did in the previous example. What is the trend in electronegativity? It should say going across a period, not group, so you can cross that out and write period on your notes. So going across a period, I'm going to pick any period, so I'll pick period 3 here, pick one on the left, one on the right. I look up my values, so sodium is 0.9 on the electronegativity scale, and chlorine is 3.2, so we see an increase. So the trend going across a period is increasing, and again, period proton pull, so it's increasing due to the increased nuclear pull. Ionization energy is the energy to make an ion. Right? How much energy is required to remove a valence electron to make it an ion? So an example here, what is the trend in ionization energy going down a group? So we can pick any group. I pick group 1. I'm going to pick sodium and let's say potassium. And we can see that the values are going from 496 to 419. If you look at another one down here, rubidium, I see that goes to 403. So the trend is decreasing going down a group, and it's due to the fact that we have more electron shells. We have 3 for sodium, potassium has 4, and rubidium has 5. So again, there's no need to memorize the trends. Use table S to your advantage and recall the explanations why. Going across a period, increased proton pull. Going down a group due to more electron shells.